In this video, I want to begin a discussion on addition reactions. And as I mentioned in my previous video on nucleophilic substitution, there are basically three types of nucleophile-electrophile relationships that are really worth considering. And this is, of course, what I mean by a nucleophile-electrophile relationship, this right here. And the first one is this. And this is, of course, the subject of nucleophilic substitution. And I did a series of videos on this subject. The second is, so we can say, the second is this. And really, this is no different. The only difference is that the nucleophile is a pair of pi bonding electrons. It is not a lone pair. And the subject here is electrophilic aromatic substitution. And I've posted some videos on that as well, which really brings us to the third sort of kind of a reaction in this regard, which is this. And this is addition. And there isn't that much difference between this and any of the others. It's a pair of bonding pi electrons that are attacking an electrophile. But the mechanisms are a little bit different throughout these three classes of reaction type. And so we really need to address them one at a time. But in this unit and subsequent videos, I'm going to talk about this third example right here, which is addition. So addition is what happens when the nucleophile is basically the bonding electrons in an isolated pi bond. This is what happens with addition. Okay, so let's start with the simplest possible Markovnikov addition of HBr across a double bond. And we will simply take this molecule here, propene, and we react it with HBr. Okay, I'm going to draw the H in red to highlight something. And we have our Br. Now again, the H is delta positive and the Br is delta minus because this bond is polarized toward the Br. So this is our nucleophilic source of electrons in the pi bond. It attacks the H and the Br leaves with the pair of bonding electrons. Okay, so the Br is the leaving group. Now in what we've drawn, we see here that the H has gone here, right? And it leaves behind a carbocation plus our Br minus. Now, alternatively, we could also show the other possibility, which is, what if the H had gone to this position, right? What if, when this double bond over here attacks the proton, why can't it go here and leave behind a carbocation at this position? Well, we can think about that logically. Here we have a secondary carbocation. Here we have a primary carbocation. And this is where carbocation stability once again becomes a primary consideration in determining the outcome of this chemistry. So let's consider an energy diagram once more. And so here we have energy on the y-axis and the progress of the reaction on the x-axis. We start with our starting materials, and it goes through a high energy intermediate state. Finally, we get our products, right? And this intermediate right here is the energy level of our secondary carbocation. So we'll just put secondary C+. And let's imagine that the primary that we've proposed would be an energy level maybe right there. So the energy level of the primary carbocation is considerably higher. And actually, it would be considerably higher, such that to get to the energy level of the intermediate carbocation in the case of the primary, we have a prohibitively large energy barrier to overcome. And so it doesn't happen. And the energy barrier of the secondary cation will happen much, much more quickly. And so this is the carbocation that is formed under these reaction conditions. This carbocation here is not formed. And so therefore, to predict the outcome of this reaction, I'll just delete the diagram that I just drew. Okay, so we finished the mechanism. The bromine traps the carbocation, and we get this product right here with the proton that was in HBr here, and I'll draw it again in red. And so this here is the Markovnikov product. That's the Markovnikov product. And this, had it gone this way, of course, we can show the bromine trapping this theoretical primary carbocation, we would have generated this product right here. And once again, I'll draw the H that in red that would have been at this position, and this is the anti-Markovnikov product. That's anti-Markovnikov. Now, the explanation that you'll typically see in undergraduate textbooks and lectures on the subject is that the bromine or the halogen ends up at the more substituted position. That's typically the way the Markovnikov rule or law is formulated, that the halogen goes to the more substituted position. Actually, there's a much better way of thinking about this, which is that the carbocation goes to the more substituted position. Why? Because the more substituted position is better able to stabilize that intermediate carbocation through inductive effects. In this case, we have two alkyl groups stabilizing this intermediate carbocation. In this group, actually, there's only the one alkyl group which is stabilizing that carbocation by inductive effects. So in other words, the Markovnikov product is the one with the more stable carbocation. And this is just another example of chemistry where we have to consider the energy level of the intermediate. And carbocation stability is a concept that comes up again and again in second-year organic. And this is just another place where we see it. And I'll remind you that carbocation stability actually has reared its head in SN1 and SN2 reactions, SN1 reactions. And here again, we see it in addition. So the Markovnikov is the more highly substituted alkyl halide, but actually the reason is because it goes through the more stabilized substituted carbocation. So that's Markovnikov addition of HBr to a double bond. And in the next videos, we'll cover the anti-Markovnikov addition using HBr with peroxides. And we'll see that the regiochemistry of that outcome is still dependent on the relative energy levels of reactive intermediates. So the same logic holds.